So today is going to be the second lecture on measurements and uncertainties. I will try to go a bit faster today, so I will request you to pay utmost attention. And we'll be looking at some examples in the subsequent sections as well. So in the previous lecture, I told you that you observe a reading on some instrument. The purpose is to measure some physical quantity. And the act of transforming a reading into measurement means that you actually want to specify what is called the best estimate of your value. What's the dispersion or spread of the values, which means the possibilities of uncertainty, how spread out is your value, and you would like to associate a probability distribution with it. And you would like to tell what confidence do you have in the best estimate and the spread that you've specified. And finally, you would like to tell what the units are. So this is a GUM approach, for the approach as propounded by the Guide to the Expression for Uncertainties in Measurement. And we're going to follow this approach in this laboratory course. Alright, so we look at a simple example. Suppose you have a digital voltmeter. Now you just take a single reading with the digital voltmeter. It's a digital scale. And suppose you are in a setting so that you observe these three significant figures and two significant figures after the decimal place. So the reading that you observe is 1.34 volts. So the GUM approach, even though you're looking at one point, you're doing a point measurement, but still associated with this point measurement is some spread. So you have to specify a spread and you have to talk about the probability distribution function. Now this is just a single reading. So you don't have to perform the experiment a large number of times. Even looking at a single point from the data set, you can specify what the spread of the values could be. So in this particular case, this 1.34 volts could in fact be any number that ranges between 1.335 and 1.345. Because if you look at all the numbers inside this range, you round them off, you will get 1.340 volts. Okay? And you're equally uncertain about all the values that lie within this range. So this range has a half length of 2 delta, and it has an interval length of 2 delta, it has a half interval length of delta. So what you could say is that associated with this reading on a digital scale, since the instrument has a finite resolution, it has a least count, it has a gradation, a minimum gradation, and you cannot measure better than that minimum gradation. So it has a finite resolution or a digital scale. So you could at best specify a spread of values. And the probability distribution function in this case is uniform because you're equally ignorant of all the possibilities. So you specify the probability distribution, you specify a spread, you have a best estimate within 1.340 volts, and what you would like to do now is to find out an uncertainty. Now in the previous class there was confusion about what these digits should be. Notice here I put 1.345 and here I put 1.335. Now how is this scenario different from this scenario? Of course it's slightly different because here on the left hand interval I am stopping at 1.335. In this case I am stopping at 1.336. Now these numbers that are numbers between 1.336 and 1.345 will round off to 1.340. So this looks like a more accurate description. But I would like to make my thing simple. So if I follow this prescription, if I make this edge start at 1.335 or 1.336, it doesn't really make much of a difference because I'm dealing with minute numbers anyway. So for simplicity, what we could do is we could use this probability distribution which gives some rounded off value of this interval, which is 0.001. This is different from this 0.009, but it doesn't make a huge difference. So let's stick to simplicity and specify this as our probability distribution function, a triangular probability distribution function that has a total spread of 0.001. It's easier to deal with 0.001 than 0.0009. So we have to stick to some level of simplicity in calculating uncertainties. We do not want to make our lives overly difficult because it's difficult anyway if you would like to calculate uncertainties properly. So this is our probability distribution function. It's a uniform probability distribution function. So what you would like to do, for example, if this is your reading, this is the distribution function that you specify. So it's a uniform probability distribution function because you're using a digital scale. And you're equally ignorant of all the possibilities. All of these possibilities can occur with equal probability, in other words. So what we do is you look at the length of this interval. The interval has a length of 0.010 volts. You take half of this length, which is the length from the best estimate to one of the edges, is 0.005 volts. And then you divide this 0.005 by under root 3. And this is your uncertainty in the reading. Alright? So the reading that you will quote in your notebooks is going to be 1.680 plus minus 0.003 volts, and you will specify that this is a triangular probability distribution. Okay? Oh, sorry, a uniform probability distribution function. Uniform. Because you have a digital scale here. You have the units here, you have the best estimate, you have a standard uncertainty, you have a probability distribution function, and you learn later that you're 68% confident about this uncertainty. If you multiply this with 2, you'll be 95% confident about this uncertainty. Now the question is, where does this under root 3 come from? I'll explain that in a moment. Okay? Okay, I'll answer questions later. We have to go fast, otherwise we'll just be carried away with question and answers. Alright, so this is what I've done on the blackboard. I have a value of 1.680 plus minus 0.003 volts. It's associated with a uniform probability distribution function, and I'm 65 or 68% confident about it. It doesn't matter whether you specify 65% or 68%. On the level that we're talking about, they're just the same. You can't see the board? Oh, you can't see the slide. Sorry. Alright, remember. Yes, just one question. So, I'll explain that in a minute, alright? Now, when I make a measurement with a certain instrument, for example, I use a digital voltmeter, for example. I use this digital voltmeter to make a measurement of a voltage. Alright, so I need a volunteer. Please come. Can you please come to the... I would like to measure the EMF of this battery with the help of this voltmeter. Right, can you just connect these wires to the battery? So what's the reading that we get? क्या reading do we get? Alright, so you're getting 9.782 volts. Now this is just a single reading, and I am not repeating the experiment a large number of times. I have the liberty of performing this experiment only once. And the reading that appears is 9.783 volts. Now associated with this single reading, there is an uncertainty and the probability distribution function. So it will be specified by a uniform probability distribution function whose best estimate is 9.783 volts, and I will find out what the uncertainty is. So this 9.783 volts will actually correspond to a uniform probability distribution function whose best estimate lies at 9.783. This is the reading that I observed. I put a 0 in front of it, so the reading would be anywhere between 9.7835 volts and 9.7825 volts. So this is my voltage axis. The length of this interval is 0.0001 volts. This is my 2 times delta. I will take half of this interval and divide by under root 3 because I have a uniform probability distribution function, and that will give me the standard uncertainty associated with uniform probability distribution. So remember, in the gamma approach, even if you take a single reading, a single measurement, there is a probability distribution function associated with it, even though you are not taking multiple readings. But there are other sources of uncertainty. And remember, this is a type B uncertainty because I am just repeating the experiment once. What other sources of uncertainty could there be? Any other sources of uncertainty? And remember, I am never using the word error, uncertainty. So what other sources of uncertainty could you think of in this insidious simple measurement of an EMF with a simple digital voltmeter? What other sources can creep in to give you an uncertain result? Temperature. Instrument might not be working properly. Is there a more accurate way of saying this? Sorry? Calibration error. But this is really one kind of calibration error that we have because there is a finite scale, there is the lowest least count that this instrument can measure. So it is an uncertainty associated with the scale. And please don't look at your mobile phones. I am here to teach for a purpose. Any other source of uncertainty? What better description can you have for an instrument that does not work properly? Remember, no instrument will work properly. Every instrument will have a certain limit. Fluctuation bad, bad contacts, continuous decrease in voltage, but that's what we're going to measure over time. Zero error is a kind of type B uncertainty, that's fine, that's a good source of uncertainty. The non-infinite resistance of the voltmeter, all of these are sources of uncertainty. And all of this is lumped together in saying that the instrument can be inaccurate. The instrument will have a certain rating. Okay? So for example, we've seen one kind of uncertainty, which is a type B uncertainty associated with the scale. And we've calculated this to be 0.003 volts. Now I've just put in one extra digit that is churned out by the calculator because I would like to use this value later. So I put this uncertainty as 0.0028. The calculator will give me more digits. I just keep one more digit than I actually need. Okay, because the arithmetic at the end I would just keep the number of digits that I really want. So I keep one more digit than I actually need. So this is the uncertainty associated with the finite resolution of this instrument. Now the instrument can be inaccurate due to temperature fluctuations, due to internal resistances having a certain tolerance, and so on. So whenever an instrument is manufactured, the manufacturer provides a data sheet. So it's a sheet like, let me show you a typical sheet. So this is a sheet that is provided by the instrument manufacturer. And in this sheet, they tell you what the best accuracy is. For example, if you measure in DC voltage, the best accuracy is 0.5 plus minus 1%. Okay? So every instrument gives you is provided with a rating sheet or an accuracy sheet. So this voltmeter that we've seen will have a certain accuracy as well. So if this accuracy is 1%, right, this is stated by the manufacturer. This means that whatever reading that you measure will be, you can have an uncertainty of plus minus 1%. So now we would like to associate an uncertainty with this accuracy. We have an uncertainty associated with the digital scale or the finite resolution, but this is another source of uncertainty. And both of them are type B because they are associated with single reading. We're not repeating our experiments. So if I have an accuracy of 1%, which means that if I read off a value 1.68%, the upper limit would be 1.680 plus 1% of this, 1.697, and the lower value would be 1.68 minus 1% of this reading. So there is another probability distribution function that I make, and again it's uniform, because there is no reason to believe that I am totally ignorant of what the true value really is. In fact, there is no true value. So my value could be spread out anywhere between these limits. And if I use plus minus 1% as my extremities, as my ultimate limits, all the values that are in between are equally possible. And that's why I put in a uniform probability distribution there. So now I have 2 delta, I find out what delta is, and then I again divide by under root 3 to find out the uncertainty due to rating. So I have 2 sources of uncertainty here. I have specified them. And no computer will tell you what the sources of uncertainty are. You have to use your mind. And you have to use the proper formalism to find out what the uncertainties are. And it all starts with defining a probability distribution function. And I'll explain where the double under root 3 comes from. So now I have uncertainty due to the scale, uncertainty due to the rating. Now I want to find the combined uncertainty. Now both of these uncertainties have to somehow add up. But generally, naively, you would like to add up these uncertainties to find the total uncertainty. But that's not how you do it in the GUM approach. You take the square of each of these uncertainties, add them up and take the square root. Because if you simply add the uncertainties, you're overestimating the uncertainty. Can anyone give me a reason why? Why don't we simply add up the uncertainties? Why is it a better approach to add these uncertainties in square quadrature? Why don't I want to add up the uncertainties? Tell. Exactly, because the uncertainties are really vectors. They could point in any direction. The uncertainties could be positive, negative, and if I'm just adding the 2 vectors, it means that they are all, I'm assuming that they are in the same direction. Both uncertainties are positive, or both of them are negative. But they really like 2 sides of a right angle triangle, so I have to add them in quadrature. And if I have other sources of uncertainty, I will add all of them in quadrature. u1 square plus u2 square plus u3 square plus u4 square under root. Now I find this arithmetic expression, and it turns out that the result is 0.010 volts. So I like to keep one more significant figure than I actually need, because then I can round off everything so that I have the proper number of significant figures to find the result. So now there are 2 ways of quoting the result. One possibility is 1.68 plus minus 0.01 volts. The other possibility is 1.680 plus minus 0.010 volts. Now in the first case, the uncertainty has 2 significant figures. Oh sorry, 1 significant figure. Just this one. And the uncertainty's most significant digit is at the same position as the least significant digit of the true value. Here I have 2 significant figures in the uncertainty, 1 and the 0. So the 0 that I have written here means something. It has a certain value, it has to be respected. So it does mean something. So I have to put in the proper digit here after the 8. So this 0 is at the same position with respect to the decimal as this 0 with respect to this decimal. Alright, so this has 3 significant figures after the decimal, and so does the uncertainty. The uncertainty, but there's 2 significant figures. Alright, so this 0 does not count as a significant figure. Alright, so you never quote more than 2 significant figures in the uncertainty. The uncertainty can have at the most 2 significant figures. In most cases, it has just 1. Now I'll give you examples of this. Now since I just calculated the u's by the prescribed formulas, and I haven't multiplied the u's by 2 or by 3, the coverage probability is given by 68%, and this uncertainty is called the standard uncertainty. And why is it 68%? Because it is reflected back to a Gaussian probability distribution function, which is the most universal of probability distribution functions, and within plus minus 1 standard uncertainty or standard deviation of the mean value, the area of the curve under the normal distribution is 68%. Now I'll explain this in a minute later. Now, how do we quote results? Now, in the first quotation here, I have 1.34 as my best estimate, and I have 0.005 as the uncertainty. Now, is this a correct or an incorrect way of stating a result? It's incorrect. Because this, even though the uncertainty has one significant figure, the position of this digit is one beyond the least significant digit of the true value. So this is incorrect. What about this, the next one? Incorrect. Because the least significant digit of the uncertainty is bigger than the least significant digit of the thing. What about this one? Incorrect. What about this one? Correct. The uncertainty here is coded to two significant digits. That's allowed. You can code one or two significant digits, and the uncertainty and the least significant digit is at the same value or is at the same position with respect to the decimal as this number. What about this? Correct. And what about this? This is again incorrect. So what I need to do here, if this is my uncertainty, I can correct this by typing 1.34 plus minus 0.02. This 0 here is nonsensical. It's nonsensical because you have an uncertainty that's much larger. So this 0 here does not make sense at all. So most of the assessment that will take place during the laboratory course will actually be how you put your uncertainties and how you put in your final results. Calculations is one matter. Keep one or two significant digits beyond your final result, but at the end you are only allowed to quote uncertainties to the proper number of significant figures. Okay, and it has to match your best estimates. Now, if I have a digital measuring instrument associated with the scale is a uniform probability distribution function, and the uncertainty U is given by delta over under root 3. Now, if I have an analog instrument, generally the probability distribution function associated with it is triangular, and the uncertainty is smaller. It's delta over under root 6. It's smaller, and there's a particular reason for that. Okay. Now suppose you have a digital scale, for example, this balance scale. Now this is a digital balance. Can you focus on this balance? Yeah, सब कुछ मिल जाता है. Now you have a digital balance. You measure something. It's a digital scale. So you will get some reading and you will associate a uniform probability distribution associated with the finite scale of this instrument. Is this copying up? Okay. So on a digital scale you get readings of this kind, 83.6, 0.62, 0.627 depending upon the sensitivity of the balance. Okay? What's the sensitivity means? What's the least measurement that it can make? Here it can measure hundreds of milligrams, here it can measure tens of milligrams, here it can measure milligrams. Okay? Now, consider an analog scale. For example, if this were measuring balance that were equipped with an analog scale, a pointer moving along the scale. That's an analog scale. So if you have the pointer between 80 and 90 and the minimum gradation is 80, 90, 100, so you don't have a final gradation and your pointer is here. It's in between 80 and 90. Now can you make some conclusion about what the real about what the value is? 82.5. Just look at the top. It's somewhere between 82 and 84. You don't have to go all the way between 80 and 90. By just observation, you can tell that it's closer to 83 or to 84 than it is to 82 or 85. So you have a greater confidence about the most probable value of the weight, of the mass. Likewise, if this is your gradation, and I zoom into the gradation here, so this is the position of the pointer. So can you tell me what the possibly the true value of this mass could be? It could be anywhere between 83.4 and 83.5. And you can just look at this pointer and use your judgment to tell that if you divide the gradation between 83.4 and 83.5 into 3 equal parts, it's going to lie in the middle part. So it's close to the center between 83.4 and 83.5. So the probability distribution that you can actually make here is not a uniform probability distribution. You are legitimate, or you are allowed, or it's permissible to make a triangular probability distribution which peaks at some values and falls off to zero somewhere else. So the probability distribution that you could make is a triangular probability distribution. For example, something that peaks at 83.45 and falls off to 0 at 83.40 and falls off to 0 at 83.50. So this is a triangular probability distribution function. And because you can use your innate sense of human judgment and observation and your visual perception to tell you what is the most likely value of the mass that you try to measure. If you don't use a uniform probability distribution, you can use with the help of your innate biological sense of choosing one option over the other to form a triangular probability distribution function. And the spread of such a probability distribution function is given by delta over under root 6. Where delta is this half interval. So the half interval here is 0.05 gram. You divide this by under root 6, you get approximately 0.02. So your best estimate of the measurement is 83.45 plus minus 0.02 grams, assuming a triangular probability distribution function and 68% confidence approximation. Okay, so a digital scale has a different probability distribution function as compared to an analog scale. Now if I have this balance here, alright, and if I measure something on this balance, right, I get 12.55 grams. Okay, now this is a digital balance which has a digital scale. So the best estimate that I am obtaining is 12.55 grams, but associated with this is a uniform probability distribution, and I can draw that probability distribution here. So since it's a digital scale, and again I'm talking about type B uncertainties, 12.55 0. This is now mass in grams. Here I have 12.555 and here I have 12.545. So I can find this half and divide by under root 3 because it's a digital scale. And this balance will also have some accuracy to it. So you will combine the uncertainty, the type B uncertainty due to the scale and the type B uncertainty due to the rating of this instrument. Alright. Now where does this under root 6 or under root 3 come from? I'm not going to belabor you through the mathematical details, but this is something that I've already uploaded. So this under root 6 or under root 3 comes from the second moment of a probability distribution function. And what this second moment means is simply the square root of the variance. Now what is the variance? If I have the uniform probability distribution function, I take the value x, from it I subtract the mean and I square it and multiply it by the height of this probability distribution function and integrate from minus infinity to plus infinity. This is the variance. It's also called the spread or the dispersion. And if I use the uniform probability distribution, I get del square over under root 3. And I take the square root, this is del over under root 3. So this del over under root 3 is just a variance or the spread or the second moment of a uniform probability distribution function. If I repeat this for a triangular probability distribution function, I get del over under root 6. So this is the definition of variance or the second moment. Second moment because I have the second power here. If I just have the first power, it's called the first moment. Now can anyone tell me, can any adventurous soul tell me what the first moment of a probability distribution function is? If I just put this equal to 1, this exponent is 1, what will this value equal to? No, this is the standard deviation. This value will just equal the average value. The mean is the first moment. The variance is the second moment. And if I put this equal to 0, the answer will just be 1, because the probability distribution function of the entire space integrated just gives me 1, because the sum of probabilities has to be equal to 1. So the variance is a measure of the spread, and this is how you calculate it. So you can go home and just look at this derivation. So this is the reason why we have under root 6 and then under root 3. Okay? It's not without good reason. Now one of the most important distribution functions that we come across is the Gaussian distribution function, or a normal distribution function. And this is the form of a normal distribution. Okay? Here sigma is the spread or the dispersion or the square root of the variance. So if you have some mean value and you go 1 sigma to the left and 1 sigma to the right, and you take the area under this region, it will be 68% of the total area under the curve. So when we talk about standard uncertainties, we are going one variance, one square root of variance to the left and one square root of variance to the right. And that's why our confidence in the true value lying in this range is about 68%. Okay? Yes? You have a question? Okay, so these are the three most important probability distribution functions we'll come across: uniform, triangular, and normal. Okay, but I've already tried this out. Okay, now let's try measuring the voltage or EMF of a battery using an analog meter. Now this is an analog meter, right? It's slightly more complicated, it looks more complicated, and remember, digital multimeters are not necessarily more accurate than analog multimeters. And another point that you might have noticed is that an analog meter can actually be more precise than a digital instrument because the uncertainty is smaller. Okay? So now slightly, can you zoom in, focus a little bit? Alright, this looks good. Now if I use, okay, I need some help here. Can you just measure this? Can you just measure what this voltage? You don't have to actually, everyone doesn't have to actually see, it's not very exciting, but can you measure this voltage? आप खुद सोचो कौन सी ये देखो ये स्केल है तो 10 वोल्ट DC is the full scale, so you look at this reading 10 is okay. Alright, can you zoom in on this a little bit? So probably you can't see properly from this distance, but what I'm seeing on this multimeter is actually something quite complicated. The arrow or the needle is between two gradations. Okay? And so let me show you on the blackboard what direction this pointer is really pointing in. Remember, it's an analog instrument. So I have 8 here and I have 10 here and there's a 9 here and I don't have 9 marked back here. So I have 1, 2, 3, 4 gradations between 9 and 10. Okay, and the pointer is pointing somewhere. pointer is pointing, I mean this is so flaky here. Very good news, chal. Can you use a different extension board the next time? So this is the position of the pointer. This is 9. Of course, this has to be 9.8. So now the pointer is somewhere in between 9.8 and 10. Now you would like to make a probability distribution function. Is it triangular or uniform? You would like to make a triangular distribution whose best estimate is 9.9. And it goes to 0 at 10.0 and goes to 0 at 9.80. Some other individual or experimenter with a more acute sense of observation can actually put this at 9.82 and this at 9.98. It doesn't really matter. So now this depends upon your judgment where you would like to taper off this triangular distribution to go to 0. What are the extremities of your distribution? Are you being conservative, ultra-conservative, or are you being liberal? So you can be social, you can take up these social norms while doing experiments. So you put your extremities at where your judgment pleases best. Okay, I am slightly conservative, so I will put this at 9.80 here and 10.0 here. So I know that my true measurement cannot go beyond these extremities. So now I take this half length, which is 0.1, divide this by under root 6. This will give me a standard uncertainty. So I will associate this measurement with a triangular probability distribution, 68% confidence, and an interval and an uncertainty of 0.1 divided by under root 6. Okay, and of course, then I have to take into account the rating of this instrument. You on it? Now we talked about type B evaluations. So you take a single reading, even with that single reading, even though you are sampling a point, but there is a set associated with it. देखो हम जब एक पॉइंट उठाते हैं किसी डेटा में से हम पूरे सेट को भूल जाते हैं. But when we are talking about uncertainties, we have to look at the set paradigm, not the point paradigm. We're not talking about point set. We're sampling values from a set of possibilities, and you have to know what the entire range of possibilities is. Okay, so this is the type B uncertainty. Now, type A uncertainty is something totally different. Now, suppose, let me give you an example. What I have here is just an inclined plane, and on this inclined plane, I'm going to slide down a marble, a steel marble, and this will impinge on a graph paper which is fitted with a carbon paper. So it's going to mark its presence on the graph paper, and I'm always going to start the experiment in approximately the same way. Now this is how experiments typically occur. You perform a measurement, the measurement changes over time. You perform a measurement again, you get a new reading. So type A evaluations are aimed at performing the experiment a large number of times and getting a scatter of values. Okay, so now let me perform this experiment. So I release this ball from a set position and it falls onto the graph paper. So I'll probably repeat this experiment 10 or 15 times. And now there is nothing inaccurate about what I am doing. It's just repeating the experiment over and over again. You can't challenge my skill here. Okay? Just 5 more times. I've made this stopper so that I'm always initiating the release of the ball from the same point. Now this is what a real experiment will actually look like. You perform an experiment a number of times, you'll get a scatter of values. Now if I just release this carbon paper, now what we have here is a set of points, and all of these points are not the same. In fact, this is an experiment in which the precision is pretty good, so I'm doing really well here. But there are these outliers as well, and all of these points do not actually match. So if I perform this experiment a really large number of times, I will get a spread of these values. I'll get scattered. So how big is that spread? Now I'm doing a type A evaluation. Let's do another experiment that is actually demonstrative of this process. Now we have a specially constructed board here. Okay? एक काम करो, पीछे से डबल लेंगे, डब्बे के साथ। So another safety mechanism you have to take into account is lifting heavy loads. Just have to be careful in lifting heavy loads. Alright, now what I'm trying to do here is with this Galton board, okay, I'm going to release these marbles from approximately the same position. You can try this on your own after the class, and what you'll observe, we have 50 minutes for the class, so what you'll observe at the end is that this will build up into a normal distribution, into a Gaussian distribution. So now, releasing these balls from approximately the same point in multiple runs of experiments, and with time what builds up is a bell-shaped curve, a normal distribution. Now this normal distribution has a certain spread, and that spread is generally called the standard deviation. So type type A evaluation entails performing the experiment a large number of times. Another experiment that you can perform on your own is possibly just having a piece of paper and throwing this piece of paper from a certain height and finding the fall time with the stopwatch. So you have a start and a stop signal. You can perform this experiment a large number of times and you obtain a spread of values. So this is something that you can perform on your own. And this is actually, you can make this into a laboratory exercise as well. So in all of these cases, what you are observing is a spread of values. Any better? It's a spread of values or a dispersion of values. Now, when I perform this falling experiment through a rolling marble on an inclined plane in the serenity of the lab without the pressure of 15 minutes, this is the actual curve that I get. Now if I look at the position of each of these points and mark the position on this gridded scale and then make a frequency histogram, I will obtain a Gaussian shape or a normal distribution curve, and I can find out the spread of this distribution. Okay, so this is a type A evaluation which entails finding the spread of the values or the scatter of the values. Now there are certain definitions you should be aware of, and I've uploaded all of this on the website, so you can go into the peace of your homes and look at this at leisure. So we can define a mean of a scatter. Mean or average is something really clear. We can define the standard deviation, which is the difference of each value from the mean squared, sum divided by the number of values, square root. This is called the standard deviation. So this is also a measure of the spread, how spread out your values are. आखिरी 5 मिनट है 10 तसल्ली से. Now there's another quantity that is of real interest. What we do in the laboratory is we find an estimate of the mean. So we would like to find out what is called the spread in the mean. This is called the standard error in the mean. Now what does the standard error in the mean physically mean? Suppose I have a large box of balls, and on these balls we have numbers written from 0 to 9, and I would like to find the mean of all of these values. Now what I can do is I can take 10 spheres out of this bucket, write down the numbers, find the mean, and have an empty bucket and spheres which are blank, and put the mean of these 10 values. So the batteries have run out. So I can put the mean of these 10 values on a blank ball and put this blank ball in the empty bucket. So this is a mean value of 10 spheres. Now I put these 10 balls back into the bucket, shuffle the bucket again, and then pick out the 10 values. And I find the mean and put the mean on a blank ball and put this blank ball which has the mean inscribed on it into this empty bucket. So this is a box of the population, and this is a box of only the means taken over sample sizes of 10. So this box of means will have its own uncertainty, its own spread, which might be different from this spread. And the spread of these means is called the standard error in the mean. Now here I have to use the word error because of historical reasons, because it's just called the standard error of the mean. So this uncertainty in this mean is called the standard error of the mean. And how do we calculate the standard error of the mean? There are formulas for this. What you do, S is something that you can find from your data. S is the standard deviation. If you perform an experiment, you get a spread of values, you get a standard deviation. From the standard deviation, S squared, N is the number of readings, you find the standard error. Sigma is the standard error. Now from the standard error, you divide the standard error by N, you get the square of the standard error in the mean. Sigma M is the standard error in the mean, sigma is the standard error, and S is the standard deviation. So from practical data, you will obtain S. S is something that you can compute from the data that is in front of you. and from that S you can calculate the standard error in the mean. So this will be your uncertainty in the mean, and this will be a type A uncertainty, and there will be plenty of examples that I will